In this example, we've got this guy who's standing in front of these steps and speaking loudly, and he's hearing a tone echoing back at him. And specifically, he's hearing this frequency, presumably really loudly. If he's hearing this frequency very loudly, presumably what's happening with that frequency?
Constructive interference.
Yeah, he's shouting, perhaps he's shouting lots of different frequencies at once, but he only hears back one particular note really loudly. So presumably that note is creating constructive interference on the echo bouncing back. And the other notes are not producing constructive interference, or at least not so much. And we want to use that information to figure out how far apart are these steps. So to begin with, I would look at the idea of what's the difference between the waves? Because for interference, you got to have two waves. If there's only one guy shouting, how is this two waves?
It's bouncing off the stairs back at him.
Yeah, and there's many stairs it can bounce off of. So if we take a look at the possible paths that can be taken by sound, we could say there's one sound wave that's traveling to, let's say, the first step and bouncing back, and he hears it. And then there's also a wave traveling to the second step and bouncing back so he can hear it. And there's also, for instance, a wave from him to the next step and bouncing back so we can hear it. But I think we can focus on just any two adjacent steps. And then the rest should probably fall in line with the same pattern. So let's start by just comparing the sound wave that gets to the first step and bounces back, and then the sound wave that gets to the next step and bounces back. Or I guess in this diagram, it's the second step and the third step. But the important thing is it's two adjacent steps. So let's call those sound wave number 1 and sound wave number 2. And if we want to look at this in terms of interference, we can use the idea of the total phase difference equation. Taking a look at the whole thing inside the sine function in the usual wave equation, the sine of 2 pi t over period, which I usually write as 2 pi t times frequency instead, minus 2 pi x over lambda plus phase constant equals total phase. But then we can apply a delta to each one of those, because what we really care about is what's the difference in total phase between the two different waves. Are they different? Are they the same? If they're different, by how much are they different? And then we can use that to analyze what kind of interference is happening. Any questions on that so far? So based on this equation, looking at the possible differences between the waves, first of all, is there anything about these two waves that is not different? What do we know is the same about these two waves?
Frequency?
Yeah, we know they both have the same frequency. In fact, it even tells us what that frequency is. And like I said, he's probably producing lots of frequencies, but only one frequency bounces back with constructive interference loudly. So we should assume that what we care about is the sound with that frequency. And since the frequency is the same, what does that tell you about this 2 pi t delta f term?
It's just 0.
Right. If there's no difference in frequency, then that delta f is 0. And also there's never really going to be a difference in time because both waves arrive at your ears at the same time. So that means this whole term is 0. And that's good to know because first of all, it means we don't have to care about it. And also it means that time doesn't matter. There's no time dependency here. We get one type of interference that stays the same as time passes. It might be different if you move to a different location, but if you're just standing in one place and creating this sound and then listening to the echo, that sound doesn't change as time passes. The only way time would matter is if the frequencies were different, if the two waves have different frequencies. And in that case, what would you observe if you're listening to two different frequencies?
Beats?
Yeah, that would be the idea of beats. And that's all about time mattering. that if you have beats, that's because the frequencies are different, which means this term is non-zero, so time does matter. Beats is all about the type of interference changing as time passes, loud to quiet to loud to quiet as time passes. But in this case, we don't have to worry about that because the frequencies are the same. So we can focus on the other terms.
So just to be clear, sorry to interrupt. So if the frequencies were different, then it would be beats, right?
Right. If you're listening to two different frequencies at the same time, then you're going to hear beats as it wobbles between loud, quiet, loud, quiet, loud, quiet, as the type of interference cycles around. And in that case, then the time term is really the only thing you need to worry about, because that's what's changing as time passes. The other terms exist, but they're not changing as time passes, so they're not as important. So generally, I would say if the frequencies are different, then the time term is there, and it's the only thing that really matters. If the frequencies are the same, then the time term is zero, and you focus on the other terms instead. Any other questions on that so far? And also, one extension of this, if we know the frequencies are the same, what else has to be the same that's related to frequency?
Is it the wavelength?
Yeah, the wavelengths are also going to need to be the same. And this goes back to the velocity equation. That velocity is wavelength times frequency. Velocity equals wavelength times frequency. We know they have the same frequency because that's given information. We know they have the same speed because they're both sound and air, and they're in the same medium. And therefore, the wavelengths have to be the same as well. So we can say they have the same wavelength. We can even figure out what that wavelength is based on the idea that wavelength should be, if we just solve for that, speed divided by frequency. Do we know what the speed of sound in air is here?
340.
Yeah, that's provided in the problem, 340 meters per second. If it's not provided, you can usually say it's somewhere around 340-ish. I think it's usually closer to around 343 or 345 under standard temperature and pressure. But 340 is what's given here, so that's what we'll use. And then frequency, 255 hertz, which is 1/seconds. So we divide those, and that'll give us the wavelength. 340 divided by 255. So 1 1/3. And the seconds cancel out, so we just get meters, or we could say 4/3 meters. So that's the wavelength, 4/3 meters. Any questions on that so far? Also, in our total phase equation, we know lambda is a constant. Lambda is the same value for both waves. What can you do with a constant inside a delta?
You can like take it out.
Yeah, any constant multiplier or divisor can be pulled out from the delta. So we can rewrite this as -2 pi times delta x divided by the wavelength. Do we know anything about the delta x? Are the path lengths different here?
For wave 1, delta x would be 2D, right?
Well, it's not really so much for wave 1. It's more comparing wave 1 and wave 2. But yeah, I think 2D should work because wave 1 and wave 2 are definitely going different distances. Wave 1 is traveling a shorter distance. Wave 2 is traveling a longer distance. And how can we tell that the difference is 2D?
Because like to go like left, it would be D, and then when you go back on the right way, it would be another D, right?
Yeah, exactly. Wave 1 and wave 2 are both traveling some distance to this step, but wave 2 travels D further on the way out. And then on the way back, it also travels an extra D further on the way back. If you're not sure, you could also set it up algebraically. If we say, like, let's say the distance to the first step is some distance, we'll just call that L for now, for the length. So this is some distance L. And then we have an extra D beyond that to get to the next step. So let's call this distance an extra D. So wave one is traveling L plus L. Wave one is traveling L plus D plus D plus L. So they're both traveling 2L there and back. Wave two is also traveling an extra 2D. So if you're finding the delta by subtracting, 2L plus 2D minus 2L is just 2D. So we know the delta X is 2D. Wave number two travels that much further. So we can fill that in for delta X. We also know lambda, the wavelength is 4/3 of a meter. Do we know anything about the delta phase constant, delta lowercase phi?
Would it be the same and then like 0 because it's from the same source at the same time?
Yeah, exactly. The phase shift is really all about the source. If you've got two sources that are like cycling in synchrony with each other, if they're both creating crests and both creating troughs, like crest and crest at the same time, trough and trough at the same time, then there's no phase difference. In this case, we don't really even have two sources. We just got one source. All the waves are coming from the same guy. So since there's no difference in the sources, we can assume delta little phi is 0. There's no phase shift difference because they're both coming from the same source.
So just for a clarifying point, so can we assume that if it's constructive or deconstructive, the phase shift will be equal to 0 because they're coming from the same like point?
Not necessarily, because whether you get constructive or deconstructive interference is not about the phase shift, it's about the total phase. So the constructive or destructive or partial, the type of interference tells you information about the total phase difference, the capital phi on the other side of the equation. The phase shift is not about the type of interference. The phase shift is about what's going on at the sources, whether the sources are synchronized or not. And the actual type of interference, the total phase difference, is the combination of information about the phase shift difference and information about the path length difference.
So could you give an example of what like a non like 0 phase shift would be?
Yeah, that could happen if you have two different sources. Like let's say there are two people shouting at the wall, but their vocal cords are not vibrating together.
Okay, thank you.
Or alternatively, if you've got two speakers that are both producing the same frequency, but they're wired differently. So like one of them pushes when the other one pulls and vice versa. So one creates a crest while the other creates a trough, then one creates a trough while the other creates a crest. That would be half a cycle out of sync. And what's half a cycle in radians?
Pi?
Right. So in that case, if they're vibrating exactly out of sync with each other, then we would say delta little phi would be 1 pi. But delta big phi, the total phase difference that actually determines type of interference, is a combination of that delta little phi and any difference in path length. So that really brings it all together. Another example would be if you're talking, let's say, radio waves from two different antennas. In that case, the two different antennas might be set up to broadcast in sync with each other. So they're both creating crests at the same time, both creating troughs at the same time. That would be no phase shift difference. Or they might be set up so that one of them is a certain fraction of a cycle ahead of the other. So that would have a phase shift difference, which either would have to be given information, or maybe you have enough other information that you can solve for delta little phi as the only unknown left. In this case, though, both waves are coming from the same source, so there's no reason why they would have different phase constants. I think the only exception to that would be if the waves are coming from the same source, but one of them is being modified in a different way from the other one. Like maybe one of them is passing through some sort of filter that modifies it to have opposite phase shift. Or if they were bouncing off of very different things. Like if one of them is bouncing off something that's harder than the medium that it's coming from in the first place, and the other is bouncing off something softer, then you could get a phase difference. But in this case, they're both bouncing off of these presumably stone stairs. So if they are changing, they're both changing in the same way. And so there's no difference in their phases. So that means we can just ignore that term entirely. No difference in phase shift means delta little phi is 0, allowing us to focus entirely on the path length term. Any other questions on that so far? And also, what do we know about the total phase difference, delta big phi?
It's like an even multiple of pi.
Yeah, if we know it's constructive interference, then delta big phi has to be a whole number of cycles. That is a whole number of 2 pi, and any whole number multiple of 2 is an even number. So that's got to be an even multiple of pi, 2 times pi times n, where n is just some whole number. And meanwhile, on the other side, we've got negative 2 pi times delta x, which we now know is 2d, divided by the wavelength. I'm just going to leave the wavelength as lambda for now. We can fill in the value 4/3 meters later if we need to. But let's just leave it as lambda for the moment. At that point, I think we have everything we need to solve for d. How would you isolate d here? What could you cancel out?
Cancel out 2 pi.
Yeah, we could start by dividing both sides by 2 pi, meaning we just get negative 2d over lambda equals n. And then if you multiply by lambda, you get negative 2d equals n times lambda. And this is a very important result in its own right, that the path length difference has to be a whole number of wavelengths. In general, this should be true in any situation where you're getting constructive interference and the only difference is how far the waves are traveling. There's no phase shift difference, no frequency difference. If the only difference is how far the waves are traveling, then you get constructive interference when that path length difference is a whole number of wavelengths. So that can often be a useful shortcut. If you know those are true, if you know there's no frequency difference, no phase shift difference, if the only difference between the two waves is how far they're traveling, then constructive interference is always going to mean whole number of wavelengths offset. And then what would be one last step to solve for d here?
Divide by 2.
Yeah. Formally divide by -2, so we get n times lambda over 2 with a negative. But ultimately that negative doesn't matter because n could be any integer, positive or negative. So we can just say, let's use a negative integer for n. That'll cancel out the negative here. In other words, d equals any multiple of lambda over 2. Any questions on that so far? We also know lambda, the wavelength is 4/3 meters. So what's half of lambda? Half of 4/3 would be, yeah, 2/3. So lambda over 2 can be rewritten as 2/3 meters. And that means d, the distance between steps, could be any multiple of 2/3 meters. So you could have 2/3 or 4/3 or 6/3 or 8/3. Any whole number times 2/3 meters would work. Since this is just asking for one possible value, I think I would just use 1 times 2/3. Because any multiple will work. Simplest one would just be 2/3 of a meter. And that sounds like probably a more realistic distance for a step anyway. You probably wouldn't expect the steps to be like 200 thirds of a meter apart. Any other questions on that?
I had a question. Like you mentioned that the different, like the difference should be like a whole number of lambda wavelength. Like I didn't understand that part.
This one?
Yeah.
Well, going back to the previous, the original total phase equation, we know that the if you have a situation where you know there's no phase difference, so this term can be ignored. Sorry, no frequency difference, so this term can be ignored. And if you also know there's no phase shift difference, if the sources are synchronized with each other, then there's no delta phi. In that case, your entire total phase equation, is going to become much simpler. So in general, if the sources have the same frequency and are synchronized, that is, if the only difference between the two waves is how far they're traveling. Let me tidy this up a bit. If the only difference between the waves is how far they're traveling, then the total phase difference equation becomes much simpler. The frequency term is gone because there's no difference in frequency. The phase shift term is gone, the delta little phi, because the two sources are synchronized, so there's no difference in phase shift. So that means the delta total phase just becomes -2 pi times delta x over lambda. And the lambda can also be factored out because it will also be constant. And moreover, the negative can be ignored as well, because the negative or positive really just depends on the order you're subtracting, whether it's x2 minus x1 or x1 minus x2. If you've got several terms, that negative is very important because it matters which order you're subtracting. You got to be consistent with all of them. But if this is the only term, the negative just depends on whether we're subtracting 1 minus 2 or 2 minus 1. So we can ignore that negative. And once again, the n could be any whole number, any integer anyway, positive or negative. So that means the delta total phase just becomes 2 pi delta x over wavelength. And if we're specifically looking at constructive, what does delta total phase have to be to get constructive interference?
Any even number integer.
Any even number times pi. So that means we're going to get constructive interference when this equals some even number times pi. But we've got 2 pi on both sides, so we can cancel that out. So we just get delta x over lambda equals a whole number. And then how would you solve that for delta x? Delta x would equal what?
N into the lambda.
Yeah, n times lambda, just multiplying both sides by lambda. So in general, in any situation where the sources are the same frequency and they're synchronized with each other, both oscillating in the same way, then therefore that the only difference between the two waves is how far they travel. In that type of case, you get constructive interference when the path length difference is a whole number of wavelengths. So that is a much simpler way of analyzing that particular kind of situation. You can always start with the total phase difference equation anyway. It'll just lead to this result. Alternatively, what if we wanted destructive interference? Instead of delta x being a whole number times wavelength, what would we get instead?
Like a fraction?
Specifically, what kind of fraction? Because a whole number also counts as a fraction. You could just write it as n over 1.
1/2?
Yeah, 1/2, or what other fractions? Like 1/2 wavelength offset would work. What other fractions would also lead to destructive interference?
Three over 2?
Yeah, 3 over 2, because that's 1.5 wavelengths. One wavelength offset would make it constructive, but 1.5, that extra and a half makes it destructive. So 1/2 or 3/2, or what else?
Five halves.
Yeah, 5/2, because that's 2.5. In general, so anything that's something and a half cycles offset will work here. So we could write that as n plus a half. So if the difference in path length is something and a half wavelengths, where n is some whole number, that will always lead to destructive interference. Again, assuming the sources are the same frequency and synchronized so that the path length is the only difference between the waves. So this is a useful generalization for those specific cases. In any situation where you know the path length difference is the only difference, if the waves have the same frequency and same phase shift at the source, then these are some very useful shortcuts. Constructive when the path length difference is a whole number of wavelengths. Destructive when the path length difference is something and a half wavelengths. If there is a phase shift difference, though, that's going to change things. Any other questions on that one? Then let's try out another example. Let me pull up a different one here. So in this one, we've got 2 radio stations. We know they're 140 meters apart. And we also know that you're standing at Ressler Hall 1,400 meters further beyond one of them. And we also know the frequency of the radio waves they're emitting. And we know that at Ressler, you're getting a radio transmission with maximum amplitude constantly, which tells you what type of interference are you getting.
Constructive.
Yeah, constructive interference at that location. So we're assuming that as the observer, you have set up shop at Ressler Hall. So let's say you have a radio receiver. You got your little radio receiver here with an antenna. And you find that you get a very good signal, maximum amplitude radio transmission. So yeah, we know that's going to have to be constructive interference, whereas if it was destructive, you'd get no signal at all. Constructive interference at this location. And if we want to analyze how that works, we can go back to the total phase difference equation. Can we use the fact that, or do we know that these are, actually, what do we know is the same here? Is there anything we can ignore in this equation?
We can ignore 2 pi t times delta f.
Yeah, this problem does tell us they both have the same frequency. It even tells us what the frequency is. Because the radio station is transmitting this frequency, 1070 kilohertz. Presumably both antennas are transmitting that same frequency. So that means we know there's no difference in frequency. Do we know anything else here? Any of the other values in this equation?
We can take lambda out of the delta part.
Yeah, since they're the same wavelength, we can factor out lambda. So we just get delta x in parentheses divided by lambda. And we can find that wavelength based on the frequency as well. Do we know anything about the phase shift? Do we know whether these sources are in sync or not?
They're in sync.
Can we tell that from the description here?
Oh wait, no.
Yeah, I don't think we can necessarily assume that. We should probably assume that there could be a phase shift difference unless we're told otherwise. Because we know that these antennas are both broadcasting the same frequency from the same radio station. But we don't really know if they're set up in such a way that they're both producing crests at the same time, or if there's some sort of offset. It's entirely possible to rig up the electronics here such that one of the radio towers emits a crest a little bit before or a little bit after the other one. So they could be unsynchronized. And in order to figure that out, we're going to have to fill in all the other information. I'm guessing we're going to have enough information here that delta little phi will be the last unknown left. Because we know, or we can find the wavelength, And what's the delta x here? What's the difference between the paths taken?
140.
Right. Because one of the waves is traveling 140 plus the extra 1400 meters. And the other one is traveling just 1400 meters and that's it. So the difference is the extra 140. And because we've got two terms here, we should be very careful about the order we're subtracting. Let's label these antenna number 1 and antenna number 2. And that way, it looks like antenna number 1 has a wave that's traveling 1540 meters. So we'll say X1 is 1540 meters. And then antenna number 2 is traveling a shorter distance, 1400 meters. So X2 is 1400 meters. And then we want to choose which order we're subtracting because we want to make sure we're consistent about the order of subtraction. Do you want to subtract 1 minus 2 or 2 minus 1 here?
One minus 2.
Sure. So delta equals value 1 minus value 2. And I would just recommend making a note of that off to the side, just to both as a reminder to yourself to make sure you're doing it consistently, and also as a note to anybody else who's reading the results or grading the problem or whatever. So subtracting value 1 minus value 2, x1 minus x2 would be 1540 minus 1400. So that gives us positive 140. So in this problem, delta x is going to be positive 140 meters. That's the extra distance wave 1 travels. So we could fill that in. Delta x is 140 meters. And then can we find the wavelength here? How would we be able to calculate wavelength of these radio waves?
340 over the frequency.
So yeah, because we've got wavelength equals speed over frequency.
It would be 3 times 10 to the 8th, right?
That's a really tiny wavelength. Oh wait, yeah, 3 times 10 to the 8th, because what speed are we actually talking about here?
Light speed.
Yeah, radio waves are actually a form of light, not a form of sound. So they travel ludicrously fast. Speed is the speed of light. Which is 3 times 10 to the 8th meters per second, 300 million meters per second. And scientific notation will be useful here, 3 times 10 to the 8th. And then we can use that divided by the frequency. So wavelength is 3 times 10 to the 8th divided by and then we know the frequency is 1070 kilohertz, means times 10 to the 3rd hertz. Hertz just being 1 over seconds. We should probably also put this in scientific notation. We got 1070 times 10 to the 3rd, because kilo just means times 10 to the 3rd. If we shift this decimal point over 3 spaces, what do we have to do with the 10 to the power? We've made this number smaller by a factor of 3 decimal places. So what do we need to do with this number to balance it out?
Increase.
Yeah, by 3 decimal places means 3 more times 10s. So that becomes times 10 to the 6th. So 1.07 times 10 to the 6th is the same as 1070 times 10 to the 3rd. You can think of that as factoring out a 1000 and then combining the 1000s to get 1 million. So dividing those, what can we do with these 10s? 10 to the 8 over 10 to the 6th is how much?
10 squared, so like 100.
Yeah, 10 to the 8 over 10 to the 6 just reduces to 10 to the 2. You can subtract the exponents. So we've really just got 300 divided by 1.07. And 3 over 1.07, does that work out to something nice? Not all that great, but wait, 300 divided by 1.07. So about 280. So that's the wavelength. These radio waves have a wavelength of about 280 meters. Rounding it off a little bit, but that's pretty close. Any questions on that so far? So if we fill in 280 meters as the wavelength, so we now have negative 2 pi times delta x divided by wavelength. What do we get when we reduce that?
We just get pi.
Yeah.
Or negative pi.
Right, because 2 times 140 is 280, which cancels out this 280. So we just get negative pi plus all this other stuff, delta little phi equals delta big phi. So negative pi plus any phase shift difference, if there is one, we don't know yet, equals delta total phase. But also, actually, if there was no phase shift difference, if we just had the negative pi and that was it, what kind of interference would that suggest? If we just had negative pi only, what kind of interference would be suggested by just negative pi? Yeah, that would be destructive because that's half a cycle. And note that this ties into what we were saying earlier about the difference in path length being half a cycle or a whole cycle. The path length difference, 140 meters, that's exactly half of a wavelength. That alone would suggest destructive interference. But what kind of interference are we actually getting at Ressler Hall?
Constructive.
Right, which means that can't be the only thing. What else is going on that changes it to constructive instead of destructive?
Is it the second?
Sorry, go ahead.
I said, is it the second antenna?
Well, you've got to have two antennas to have any sort of interference at all, because we've got two waves. But what's the other difference between those two antennas? There's a path length difference. There's got to be another pi somewhere, right? If we've got negative pi, that alone would suggest destructive interference. There's got to be another either plus pi or minus pi to get it to either 0 or 2 pi. And it looks like that can only come from the phase shift difference. So this conceptually, it looks like the path length difference alone would suggest destructive interference. There's got to be something else going on to make it constructive instead. And that something else is the phase shift difference. These antennas would have to be out of sync with each other by a certain amount to make constructive interference instead of destructive interference at this location. We can see that algebraically as well, because if we know we've got constructive interference, delta phi has to be a whole number multiple of 2 pi times n. If you then solve for delta little phi, you would add pi to both sides. So we get 2 pi times n plus an extra pi. If you factor a pi out of these two terms, what's left? Factor out pi, and what's left from these two terms? Yeah, 2n plus 1. So that means that there has to be a phase shift difference. It has to be equal to 2n plus 1 pi. And conceptually, what kind of a number is 2n plus 1?
Odd.
Right. There has to be a phase shift difference. It has to be an odd multiple of pi, which among other things means it can't be 0. And what's the easiest odd multiple of pi to use?
1.
Right. So we could use any odd multiple of pi, but to make the calculations easier, we'll choose 1. So delta phi equals 1 pi. So that means these two antennas are out of sync with each other, and they're out of sync by exactly half a cycle. One of the antennas is creating a crest, while the other one creates a trough at the same time, and vice versa. So I think we now know everything we need to know about these two antennas. They're both producing the same frequency, 1070 kilohertz. They're out of phase by exactly half a cycle. So we'd say delta phase shift equals 1 pi. Any other questions on part A?
Wait, so we're still getting constructive interference, but it's just that phi naught is pi, right?
Yeah, or the difference in phi naught is pi. That is, the two antennas are out of sync by half a cycle. And I think a good way to think of this is that if you look at this as the two components to the total phase difference, you've got the difference in path length and the difference in phase constant. The difference in path length is an extra 140 meters. How much of a cycle is that? That is what fraction of a wavelength?
Half.
Right. So that means the two waves differ by half a cycle worth of distance traveled, but they also differ by half a cycle worth of synchronization. The two sources are out of sync by half a cycle. So you've got half a cycle of distance offset and also half a cycle of synchronization offset. Half a cycle plus another half a cycle is a whole cycle. So that brings it back to constructive interference. Either one of them alone, like if there was only the path length difference of half a cycle or only the phase shift difference of half a cycle, would produce destructive interference. But combine them, you got half a cycle plus half a cycle, that's a whole cycle. And that gets you back to constructive interference.
Got it. Thank you.
You're welcome. Part B is also talking about different locations along the path. Let's say we move the radio receiver to a new location. Let's say you walk some distance towards the antennas. So let's say instead of 1400 meters, these are now going a different distance to your new location. At this point, if you travel closer, now what is the path length difference? What's the difference between these two new paths?
It's still 140.
Right. The longer one is still traveling exactly 140 meters longer than the shorter one. Moving closer or further doesn't change that fact. So you could move to any location along this path, and the difference between the two path lengths is still 140 meters. If you move off the path, that could change things though. For instance, if you travel to here, then now we'd have this path, and I'll have to redraw this one because it's vertical. That path and this path. So now we've got some different angles involved, and we need some trigonometry to figure out how different those paths are, or just measure it with a yardstick or something. But the fact that there's now this offset in angle means that it's not just a straight 140 meters again. So if you're off of that path, then things change. But as long as you're on that path, the difference is going to be 140 meters. And then for part C, it's asking for one other frequency. So I think we could go back to the original, keep everything else the same. Delta X is still 140, delta phi is still pi, but we want another, I guess we could say another wavelength. Find another wavelength that leads to a different even multiple of 2 pi, or whole number multiple of 2 pi. So find another, assume wavelength is now unknown, but set delta total phase equal to another 2n pi. Solve for wavelength, then convert that back to a frequency. And that'll give you another frequency that still produces constructive interference. Any other questions on that?
So for B, the answer is as long as it's the same path, then the distance will always be, the delta X will always be 140 meters. But as soon as you diverge off of it, it's going to be different.
Yeah. You would also run into problems if you were, instead of beyond the second antenna, let's say you were somewhere between the antennas. In that case, one of the paths is this far, and the other path is this far. So now the difference would no longer be 140. Instead, the two path lengths would add up to 140, but you'd have to work differently to find the difference in path length.
Okay. And then for C, what did you say C was?
Well, we still want constructive interference. So we still want delta capital phi to be some even multiple of pi. Let's say we make it 2 pi instead of 0, or 4 pi or 6 pi, any even multiple of pi will work. And we still want delta little phi to be pi. The antennas are still unsynchronized by the same amount. But we want to find a different frequency, which is going to mean a different wavelength. So what I would do is set up the equation exactly the same delta little phi of pi, a different delta capital phi of some other whole number of cycles, some other even multiple of pi, and then solve for wavelength. That'll tell you another wavelength that would still give you constructive interference. And then you could convert that to a frequency as well, using V equals lambda F.
So the only thing you change is the total phase constant. I mean, the difference in total phase constant.
Yeah, to a different whole number of cycles. So maybe 2 pi or 4 pi or 6 pi instead of 0 pi.
Okay, thank you.
You're welcome. All right, I've got to get going, but try out some more examples using these same sorts of approaches. Let me know if you have any other questions, and I will see you next time.
Thank you.